I am back in California, back in my office, and we are going to have a few videos where we talk about confidence intervals. So let's get right on it. Over these videos, we have four things I want to cover, and today we're going to cover one or two of them. The first one we're going to start with is defining point estimates, standard error, confidence limits, and margin of error. So let's talk about that. And then we'll get into interpreting confidence interval estimates. In another video, we'll talk about the types of estimates and when to use which one and how to do everything with Excel. Estimation, and more specifically confidence intervals, is determining likely values for an unknown population parameter. Remember what a parameter is? Should watch the other videos. The point estimate is the best single value estimate for a parameter. So if we take a sample and we get the mean for that sample, then that's the best estimate that we've got for the population mean. And the confidence interval is a range of values for that parameter. And it is the point estimate plus or minus a margin of error. And you've probably all heard that in the news where they will say something like the approval rating for this candidate is 53%, but the approval rating for the other candidate is 49%, and the difference is within the margin of error. What do you mean by that? Well, now you're going to wish you read the chapters on normal distribution and sampling distributions, because we're going to talk a lot about Z and T today. And if you already read those chapters, give yourself a big pat on the back. To estimate a confidence interval, to get a confidence interval, which gives you an estimate of what the population parameter would be, you take the point estimate, say a mean, plus or minus the margin of error. And that would be the point estimate
minus Z or T times the standard error, and plus Z or T times the standard error.
Now, why Z or T, and when it doesn't matter? We talked previously about how when you don't know the population standard deviation, you're going to have more error in your estimation than when you do know the population standard deviation. So if you don't know the population standard deviation, you use T. If you do know it, you use Z. But the larger the sample is, the closer T is to Z. So you can see here, for example, when you have 5 degrees of freedom, remember degrees of freedom, also from a previous video. So let's say you had 6 people in your sample, it gives you 5 degrees of freedom, and your T value is 2.571, and your Z value is 1.96. But if you have 1,000 people in your sample, your T value is 1.962, and your Z value is 1.96. If you even have a modestly large sample, say 100 people, your T and your Z values are pretty close. The point is that you should, if you don't know the population standard deviation, use T, but in any very large sample or even pretty large sample, it's not going to make a whole heck of a lot of difference, because once you get past smaller numbers, like 5 or 10 or 20, the T and the Z are going to be pretty close. If you do have a small sample, you better be using that T. Nice thing too is most statistical packages will, as we'll see, automatically use the right test. The confidence interval estimates, as I said, is the point estimate plus or minus the margin of error. And that may be the point estimate plus or minus Z times the standard error, where Z is the value from the standard normal distribution for the desired confidence level. If you want 95% confidence, which is standard, you'd use 1.96. If you wanted 90%, I wouldn't advise it, you would use a different number. If you wanted 99%, you would use a different number. But Z is the value that 95% of the distribution, as you know from the other chapters, is going to fall within that range. And the standard error of the point estimate is going to vary depending on, is it the mean, the proportion, whatever the parameter is that you're estimating. Let's go through a little bit of example here. There's a 95% probability that the population mean, right there, that mu, is between the sample mean, this X bar, minus 1.96 times the standard error, which is the standard deviation over the square root of n, and the sample mean plus 1.96 times the standard error. A super simple way to think about it is 95% of the time, the true population mean will fall within approximately 2 standard errors of the obtained value. And yes, I rounded 1.96 to 2. So if your mean is 6 and the standard error is 2, your confidence interval is from 2 to 10, about. If we're estimating confidence interval for the mean, we're assuming there's continuous outcome, right? It's age or test scores or something like that. It's not proportions, it's continuous outcome, and you have one sample. If we know the standard deviation of the population, then we would take the sample mean plus or minus z times the standard deviation over the square root of n. So plus that z times the standard error minus z times the standard error, that's your confidence limits. If we don't know the population standard deviation, which we often don't, we would use the same formula, except instead of z, we would use t. And we would find the t in a table using the degrees of freedom, which for the mean equals n minus 1. Now, actually, we say that, but if you are using most statistical packages, it will automatically find the degrees of freedom for you. Remember, I say this because this is a problem, an error that I've seen many students make over the years. The standard error is the standard deviation divided by the square root of n. It is not divided by n. See, it's right there. Standard deviation divided by the square root of n. But I can't tell you how many times I have seen people calculating this and mistakenly use n, so that's why I'm just reminding you again. Let's step through an example. We have the 2019 National Assessment of Education Progress reading scores, and I have the scores from the National Center for Education Statistics of 600 South Dakota Native American fourth graders. So this is the actual mean for 2019 of this sample, and it was 190. The population mean was 220, and the population standard deviation was 39. So in this case, I actually do know the population standard deviation. So we're going to use our formula, the sample mean, 190, plus or minus z times the standard error. And z, we want a 95% confidence interval, so z is 1.96. The standard deviation population is 39, we already had that, and 24.5 is the square root of 600. So we have 190 plus or minus 1.96 times 39 divided by 24.5. And that gives us 1.96 times 1.59, and that's 3.12. So our confidence interval is going to be 190 minus 3.12 is going to be the lower confidence limit, and plus 3.12 is going to be the upper confidence limit. And that gives us 186.88 to 193.12. And the important thing here is since 220 does not fall between 186.88 and 193.12, we conclude that the mean reading achievement for South Dakota Native American fourth graders is not 220. In fact, that it falls in that interval from 186, 187 approximately, to 193. So substantially below the population mean of 220.